Hello everyone, welcome back. Let us continue our discussion on reinforced concrete design. And this is the final week where we plan to discuss multiple topics and the list was given to you. So we are in the third lecture. In this lecture, we are going to model a full-scale building. Now, you can see the front elevation of this building. It is a two-storied building and the building is having a frame structure. We are going to model this using finite element framework. Now, in this course, we are not going to study finite element method, but we'll see how we can use the software to model this complete building, and we can do different types of analysis that are necessary for design. Now, for this building, it is a frame structure, and then we will construct the building model using different types of elements. I will explain that as we progress. And for this purpose, we are going to use a commercially available software called STAAD.Pro. Now you can see the ground floor plan of the building, and this plan shows the column locations which are marked red. Now if you look at the column geometry, there are different types of columns available, and we will actually model those cross sections. Not only that, you can also notice that the dimension of this building is 62.95 meter along X, and along Y it is 28.5 meter. It has the grids which are also marked, as you can see, 1 to 11 at the top, and then A to F in the vertical direction on the left hand side. Now this is the first floor plan. Here you can see it is academic building, and therefore there are different labs, and for the labs actually it has double height. That means the rest of the building is having 3 meter height per story, but for the labs it is having double the height. Not only that, there are other lift course, as you can see, and the stair also you can notice it has a 3-flight stair with a central well, and the lifts are made of walls, concrete walls. But in this analysis, we are not going to model those details. We will actually make a frame made of columns and beams. And every floor level, we have a slab. But in this analysis, we are not going to model the slab, but we'll add the mass of the slab. I will show you as we progress in this modeling. Now, one thing you can notice, just beside this YY line along grid 5, and here you can see that blue dotted line that shows the location of an expansion joint, because in that direction the dimension of the building is 62.95 meter. So thermal stress may be high in that direction because of the dimension, and that's the reason in between there is an expansion joint which is sufficient enough to allow the movement. Now if you notice the column locations, you can easily sense that there are actually two different buildings with a gap in between marked by this blue dotted line. So what we are going to do is to model the right side of the building, and for that we can identify this grid dimensions. We will create that grid as we progress. You will see. One more thing to be noticed here, if you look at the right part of this blue dotted line, this part is not purely symmetric. So this point we will further explore when we'll go to the modal analysis. We'll see its impact. We'll see that there will be some torsional modes appearing because of this asymmetry in plan. In most of the real life structures, we have this type of asymmetry because of the functional requirements. Now, for the time being, you can notice the column dimensions, and as I said, the grid locations for this right part of the building is clearly shown. Now, we'll make some assumptions while modeling. We can actually go for a very detailed analysis. As you can see, the lift core is not shown here. We will not model those vertical walls made of RC concrete. They behave like shear walls, but we will not model that in this analysis. We will make it simple so that you can follow. So we'll construct the grid points. So the sequence of modeling will be first the locations of the columns that we'll make from the grid points. Then story by story we'll create first the columns and then we'll connect the columns using beam element, and that will form the beam. And that's how we will develop the model in the vertical directions. Those who are interested, you can also explore the stiffness method or matrix method of analysis. That will also give you an idea how these models are made. And as you advance in your curriculum, in the fourth year, normally you have finite element as an elective course, and normally at the master's level, we have that course that clearly tells you how to model this type of building in finite element framework. Now, as I said, we will not model the slabs. Here you can see these green lines, they are the beam locations. So you see the ground floor beam layout, and then there are two different of markings are there. So you can see the green lines, and here along this line you can see the expansion joint. As I said earlier, we will develop the right side of the building and not the left side. Now in this part also we have this green lines and blue lines. So green lines are main beams and blue lines, if you can see, they are secondary beams. Now because this is a demonstration session, here we will not prepare the exact blue lines. For example, you can see this grid here, just right to this grid 7. There are a lot of blue lines there. We will approximate those with two secondary blue lines. As you progress, you will see that. However, you can prepare a very detailed model as per the dimension if you follow the steps we are going to adapt in this modeling. Now you can see these grid locations. However, at this point there is an offset of the green beam that you can see. It is not centrally placed over this column. You can actually model with an offset, but again, because this is a simple demonstration, we will create a grid line along that 7 and we'll make an approximation of grid locations there. However, as I said, you can further modify if you follow the same approach, and for every green beam you see they are actually flushed with the outside of the column, and you can have a very detailed model with that offset. It is quite possible. In fact, those offsets also introduce additional moments over the column, and if you recall, at the design stage we actually discussed how these bending moments are developed at the columns, and in fact in this week in the second lecture we discussed the modeling of columns with biaxial bending. Now as you can see, we will develop the beam model. We will use 3D beam element for the complete modeling of this structure, and using that beam element we will completely solve the frame structure. Now one thing you must remember that we can add the floor as a plate element. So each floor slab we can add as a plate element, and or shell. Accordingly we can model and do the analysis, but here we will show you how to apply the floor load, and that load will be distributed over the beam. As you can see here, we have a opening space for the lab with double height. So at the respective level we will apply the floor load, and as I said, we will model this tertiary beams. Okay, and for that we will make an approximation here. We will not make a very detailed model, but at this grid point we will have two tertiary beams. So the floor load again is distributed according to the nature of the slab. If you recall, we have two different types of slab depending upon the dimensions. It may be one-way slab or it may be two-way slab. So accordingly the loads are distributed. When we will apply that load, you will see, I will explain that also at that time. But keep in mind that floor loads are applied over the beams and these lift cores are not modeled, right? The cross marks, as you can see here, that means there is no slab at this floor level. That is a general marking. It is followed in the drawing. So now let us start modeling. As I said, we are going to use STAAD Pro, which is very popular in India. Now here we are going to create a 3D model. As you can see, we need to select the units of length and force, and then the model name and the directory where we are going to save the model. So we select the appropriate unit for length and force, and then we add the type of element we are going to use. As you can see, we are going to use beam element, and then we initiate the model building. So we have to create the grid points according to the column location. For that, we refer the grid points, and from this drawing we get the grid locations, which shows where in plane the columns are located, and accordingly we enter those coordinates. So you can see the dot marks, those are the column locations. As per the grid points, you can see on the right hand corner. So we repeat the process for other column locations. And accordingly create the complete grid for the ground floor. So once we join these points, we create the connection between 2 points. And then we can copy it you can see the direction of x, y and z axis. So y is vertical, and then we can copy and then you can see the grids are prepared. Now at this level we have a offset, so that point can be created based on the dimension from the drawing. So you can see there, these are the 2 points. There will be another point just right to the one created. And then again, we connect these 2 points to create a beam. Now we can copy this entire line and then here you see we have additional column locations. So this column locations are created. One is created, another will be copied, and it will be created on the right side of grid marked 6. You can see the new point. Accordingly, along that line, other points are also created. So the last point we have to create now based on the dimension. Now it is done. Again, we can connect this point and create the beam element. So you can see this blue line, that is a secondary beam. We'll model that once the complete grid is created, then we'll model that. So now we can copy this last grid line. So we copy the center line to form the next grid. So from the dimension again, we can see it is at 5.5 meter. Again, notice the orientation of the axis. We have to copy along Z, and we can copy twice to form two grids. And now you can see now this last one we have to create. So there are some additional columns here. As you can see, those are circular columns. We have to create those points as well. So that lateral dimension is 4.7, as you can see, and the next one is 5.15. So now you can see another column point is created. So the next one is also created, as you can see there. And at this corner again we'll connect these beams and we'll make a straight beam. That corner, it can have a curved geometry also, we can create that. However, for simplicity, let us create. See, the corner beam is a curved beam. However, we model it for the timing as a straight. Now we copy in the vertical direction. Y is our vertical direction. So along this direction at 4 meter we copy. So the story height is 4 meter. Now first we have to create a 2 meter high. This is actually from the ground floor to the foundation level we have 2 meter short columns. So that's the reason we have in the -2 direction we have only the columns are extended. Now you can see we will provide the supports at the bottom. So all are fixed. Now we have to assign that support. We call it support 2. And at this bottom points, which are now marked red, we will assign the support. In some of the analysis, we also model the foundation along with the soil springs below if we go for a soil structure interaction analysis. But for the time being, we assume full fixity at the foundation locations. Now, the first story, that is at the ground level, is created with a 4-meter high column, and you can see that is created. It is a 2-storied building, so we'll copy it once more. In the positive y direction, and the story height is 4 meter. With links, otherwise it will only copy the beam. So with the column, it is going to copy. It actually extrudes. So now we have the complete frame structure ready. Now let us select the layout at the ground floor. And here you can see this is the main beam. Which is actually landing over another beam. So for that, here we'll extend that line. So let us first divide this beam to create a node at the middle so that we can extend the other line and create a beam which is landing over this beam marked red. It is here. So you can see the dimension. So let us divide this line into 2 parts. For that, we insert a node point in between. And now you can see a node is created in between, and then we can connect these 2 nodes to create a beam which is landing over another main beam. There is no column. Now we will create similarly the secondary beams marked blue. And here, as I said, we'll make some assumption. We'll not create that finer details you can see at the top right corner. So we add a new point in between. You can see it is there. So you have to copy that 4 times. At a distance 5.5 meter. So it creates that intermediate beam. Then we have to repeat the same process for the secondary beam marked blue in the next grid. For that again, we have to create the new point in between. So we divide this beam in a similar way. And the point is created. So we'll copy that four times along z direction, and the distance is 5.5 meter. You can see the grid marking. It is in the positive z direction, so we link the steps. So now the beam is created. Now we have some additional secondary beams, you can see. We'll create them in a similar way. So we'll copy it twice. You can see the point. Now the grid distance is 6 meter. So the next point is created. And now that line is ready. Similarly, the other secondary beams will be created. So from that grid dimension, we can divide that green line and create the point, and accordingly we can create the secondary beams. So the point is created. We have to repeat it once more. These two beams are done. Now we have to create the other beam. So we'll repeat the same procedure. In fact, you can repeat the same procedure to create those finer details. That I leave it as an exercise for you. So I'll create this one. Again, we insert a node. So you can see the dimensions, and accordingly we have to copy. So this time, instead of copying, we again divide this line also, which will create a node there, and then we can connect these two nodes and create a line. Similarly, for the next grid, again we divide the beam. Now we can see all these new points, and if we connect them, the beams are created. These are all secondary beams. As you can see, they are marked blue. So we have to create additional beams there, but here, as I said, we'll not go for those finer details. We will just create two simple beams to demonstrate you how to create those secondary beams. So you can see the dimension of the grid, it is 8 meter. So we set these points in such a way that two intermediate points will be created. Here you see one is created there, and then this beam also we have to divide accordingly. So we can copy this along positive Z and we can create a beam. So this beam is created. Here we will make an approximation. So here you can see the dimension is 5.225 meter and the grid is 8 meter. So we can divide that line and accordingly we can create a point in between. You have to set these dimensions properly so that it is as per drawing. So now this node is created. However, if you look at the actual drawing, there a lot of other additional beams are there that we simplify with two beams. Here you can see we just have two beams in the Z direction. Now the grid is almost ready. So you can see the complete frame is now ready. So the ground floor grid is ready, and the first floor level there is no slab, and here is an additional beam as you can see. So at the first floor level we have to modify accordingly. So the first floor level, you can see there is a change in grid locations with some additional beams at a different point is there. Now this is copied in the negative z direction. So you can see the point created. So again, we copy along the negative z direction this point selected. So you can see the new point. Now we will connect these lines to create the secondary beam. This point is also copied along the negative z direction. So you can see the dimension and accordingly we can create the point. So now this point is created. So let us connect these points to create beams. So you can see they have double height. So these beams are not there. So we now delete these beams. So that will create the space for the lab as per the structural drawing. Here is another secondary beam marked blue, as you can see in the drawing. And we can go for the finer details as I told you earlier. In fact, at the corner we have a curved beam. We can also create a curved beam, but again we will not do that. We have already created a straight beam. We can see the beam is there. So let us create the points and the beam, the secondary beam. We have to copy it twice, and now it is ready. So we have the complete frame ready. So we have selected the roof label. So at the roof level also, we have to see the modifications needed. So at the roof level, these additional beams are created. So once you select this, you can also identify the beam numbers. I'll also show you the um, text file for this model, and there you can actually identify these beams based on their numbers. Okay, so now you can see the complete model of the frame structure. Right, of course, there are some approximations. You can take this forward, you can actually create a very detailed model with exact geometry. You see, if we select the beam, we get the beam number, and that we can also cross verify from the output and also the text file. So now we have to define the cross sections for beams and columns. So because this is a design problem, as a designer, our task is to propose the cross sections. So you can propose it here. In fact, we'll do the design based on that, and we'll see if the section fails, we have to increase the size and change the parameters, other parameters, maybe the steel or grade of concrete accordingly. But for the time being, let us assume the cross sections, and you can see we have selected the concrete as our material, and the section names, you can see it is 500 by 650 rectangular section, and then accordingly we propose other sections, and then we have to assign, because now we have created the model, but this model has no sectional details. So for each beam and column, we have to provide the sectional details. We can use different types of concrete. That is also possible. We have to define two different concrete properties, and then here from this drop down menu of the material, we have to select appropriate material. Right now we have one concrete material that we are going to use. So you can see different cross sections are created, rectangular cross sections of different dimensions, and then circular cross sections. Now we have to apply these cross sections. So we can select the element and assign it. We'll see in a minute. We can select the columns, we can select the beams, we can also select the beams at the floor level, as you have noticed. Now these are the columns. So now for these columns, we have to apply the appropriate section property, and we can have different section of the column at different story level. See the sectional property selected, and we assign it to the selected beams. So because we use 3D beam element for columns also, now for these columns, you can see R1, that is a section mark, and that is applied. Accordingly, we have to assign the sectional properties for other structural components. So these columns also have R1 as their section property. So we select second section property and then assign them. Now we can see R2 section property is assigned. So we apply circular cross section to these two columns. You see R3 is marked there. So you can see column cross sections are applied. These columns are still left with. So we have to select them and assign the appropriate section properties. So you can cross check whether all the section properties are applied or not. So we deselect that portion because At the ground floor level it is there, but from first floor onward it is not there, so we delete it. So now we have to define the beam sections and we have to assign them accordingly. So we select all the beams along X. First we will assign the main beam. So now they are assigned. Next we have these secondary beams. So we can assign a different section property if we plan so. So as you can see here, these are the secondary beams having R6 as the section property. So you can see here the beam numbers along with their node numbers and the property reference. Now you see at the ground floor level, the sectional properties for all the beams are assigned. Next, we can go to the first floor level and repeat the same process to define the section properties. So these are secondary beams. So the first floor level is ready. Now at the roof level. Again, repeat the same procedure. So you can see the different section size we have used. As I said, when we will go to design, we'll see whether these sections are sufficient enough. If not, we are going to change it, right? So you can see the complete frame is ready. It is made of 3D beam element, and the number of elements are automatically selected. We are not going into the details of that. That will be covered in the finite element theory. For the time being, we can consider the default option set in the software. However, we can model a single beam using a number of different beam elements. So this element was actually earlier left with. So let us assign the section property. So this is R6. So now you can see. And from this 3D rendering, you can see the cross sections of the column and their orientation also. That is extremely important because you can change the orientation of the column cross sections just by looking at that 3D rendering. In fact, you can also change the beam cross section if the need be, and if it is wrongly assigned, then from that 3D view, you can see we have the slab loads also evaluated in this Excel file. So we will apply each and every load one by one. And again, we go back to the main model, and as you can see, all sections are marked. Those are assigned. So our next task is to apply the dead load and live load. For that, again, we have evaluated the additional loads due to walls, right? Okay. So now let us assign the load. So let us add the first load case. You can see the load number. So dead load. So it is defined now. Similarly, let us also define live load. So the load cases are defined. Now we have to apply this. For that, let us edit. You can see self weight, and it is acting along y direction because y is our vertical direction, and we have applied a factor of -1. So it is applied along negative direction of the y axis. Now, first select the load case, and then for the entire structure, we have to apply the self weight. So it is assigned to the complete structure. And as you can see, this red mark shows that the dead load is now applied. Now, once the dead loads are applied for beams and columns, next is we have to apply the additional loads due to walls. And for that, again, we have major wall and minor wall. So for that, we apply a uniform load over the beams with a negative sign because it's in the negative direction. So you can see the major wall and the story height is 4 meter. So let us change it to 4. And now the load per meter run, as you can see, 16.975. So we can apply 17 kilonewton per meter, slightly higher to be in the conservative side. So let us assign that load. For that, here we define the magnitude of the load. It is acting in the negative y direction, as you can see. So it is now defined. Similarly, for the minor walls, the load is 8.575. So let us apply 9. Now for the parapet wall with 1 meter high, the load is 4.8 kilonewton per meter. So let us apply 5 kilonewton per meter. So three different loads are defined and then we have to apply one by one. For that again, we select at the story level all beams. So the ground floor level beams are selected now. And then for the major beams, we have to select them and then apply. So this can be done in a different way. So we select all the beams parallel to x-axis and then deselect those where we are not going to apply this load. Otherwise, we can assign to view. Now all these beams are selected which are parallel to x-axis. So the load is now selected. It is assigned to the selected beams. And you can see the uniform load is applied now. Similarly, we have to assign the loads for other beams. Now we select the beams, major beams, parallel to z-axis. Then again assign the load. Now the remaining beams at this floor level are selected. These are secondary beams having less load. Then we repeat the same exercise for the remaining two floors. So the process is same. At the first floor level, these beams are not having any load there because that section stops at the first story level. So let us assign the load. Now it is applied. Then the remaining beams are selected. Now at the roof level, we have to apply the parapet loading. Here you can see at the first floor level that additional part on the right hand side, it is not there, and this part also not there. So let us delete these beams. So you can see at this level we have the loads applied, but this floor will have no load there. So we modify that loading condition. That's the entrance of the building. So it is only at the ground floor level, as you can see from this figure. Now we are going to apply floor load because floor slabs are not modeled. Here you can see the dead load for the floors are estimated. So that floor load is applied as a pressure. Again, it is acting in the global y direction. So we can define this floor load using this minimum and a maximum range. The range should be 3 to 4. Slab height is 4 meters. Now you can see the load is applied. The point to be noted here, you can see depending upon one way or two-way slab, the loads are distributed accordingly. So at the first floor level, the loads are applied. And in a similar way, the second floor or the roof level loads are also applied. Now we have to apply live load. So the live loads are defined for the two different levels, and now they are also applied. So we can now run the analysis. So the static analysis is done. You can see errors 0, warning 0. So we can see the output. Now for that we go to post processing, and then we have two different load cases. You can see dead load and live load. And for that, if you select any node, and the displacement for that particular node along with the node number is highlighted. So we have the response at each and every node, and you can see the 3 different displacements along with rotations also are provided for the dead load and live load case. Because we have 2 different load cases, dead load and live load, we have the results for them. We can also define a combination that we'll see in the design class. Now, if we select beams, as you can see here, we can identify the moment and shear force. So if we identify a beam, that beam is selected and you can see it is 267 beam number. And for that, again, we have force and moments along 3 directions. And out of that, you can see MZ is the direction we are interested. And for that, we have the bending moment and also shear force, you can see. Now here is the plot for bending moment and shear force. So for any beam, if we select, we can find the displacement and the shear force bending moment. So for column also, you can see the moments and the forces are shown here on the right hand side. Likewise, for every column and every beam, we get the response due to the applied dead load and live load. Now, stresses are also provided, as you can see. In fact, for each and every beam and column, we define the cross section, and for that particular cross section, you can see on the right hand side here the stress values are provided. We can define a particular point, and as you can see, if we change the coordinate, we get the location, and at that particular location, the value of the stress is also shown. So we can repeat the same exercise for any other beam or column, and then accordingly we can find out the stresses at the surface within the cross section, and the values are also highlighted in this table. So we get the beam number, it is 221. As you slide this over the element, we get the cross section, and that particular cross section we can identify the stress at a given point. You can see on the right hand corner at the top, the YZ in local coordinate is showing the plot, and for that stress value is also reported. And you can see maximum and minimum values of stress. So we can plot the shear force, bending moment, and the displacement. These are the reactions. So at any point, if we design the foundation, we can get the reaction transfer to that foundation. So you get the forces and moments. Of course, for the design, we have to make a load case as per our codal provisions that we'll see in the next class. Here you can select different load cases and for each load case, the support reactions are provided. We can select any other support and that will be highlighted, as you can see. So that completes the discussion on the modeling. So we'll continue in the next class and we'll see how we can design that structure. Thank you very much.